Hello, in this video we're going to talk about ethanol production. Ethanol being by far the most important alcohol, as it's got many uses. Not only the obvious one in drinks, so I've got a picture of the grape up there, but also in drugs as a intermediary, in perfumes and aftershaves as the solvent. But also in various industrial products like detergents and inks and coatings. It's used in the production of all those products. So an important alcohol, not the only alcohol that's used, of course. Methanol is also quite important. Methanol is made from methane, and that's used as an intermediary to make lots of other organic molecules. So when we look at ethanol production, we're going to look at these facets. How to make ethanol is the first thing we're going to think about, and there's two methods. The first method is to hydrate alkenes, so we'll have a look at that and the mechanism that's involved in that. Then the alternative method is to ferment glucose, like the glucose that you get in a grape, for example. We're going to ferment that to make ethanol. See how we do that and the reaction conditions involved. And also we're going to have a look at biofuels, because bioethanol is an important biofuel. And we're going to have a look at carbon neutrality and the issues about carbon neutrality and whether it's actually carbon neutral or less carbon neutral. So that's what we're going to do. So let's start off with hydrating alkenes. Let's start off with the general equation for this type of reaction, and so we're going to start off with our general equation for our alkene, CnH2n, right? And hydrating implies we're adding water, so there's our water. We've got a equilibrium reaction, and we're going to make an alcohol. The general equation for the alcohol is CnH2n plus 1, and the functional group OH. Okay, so this, you can see you're starting off with two molecules and you're making one molecule, so it's an addition reaction, and we can call this an electrophilic addition reaction. Electrophilic addition reaction. We'll see why it's electrophilic addition in a second when we have a look at an actual reaction. And we're going to use a hydrogen, a catalyst, an acid catalyst to do this. Okay, so when we're going to have a look at the mechanism, let's have a look at an actual reaction with real products instead of general equations. So we're going to use ethene. So here's the equation for ethene. We've got CH2, CH2. We're going to add water to it. And we're going to use a phosphoric acid catalyst. Right? So the formula for phosphoric acid is actually H3PO4. And that occurs. We'll do the reaction conditions in a second. We're going to make some ethanol, which is CH3, CH2, OH. Okay, and we're going to do this at temperatures such that the ethanol produced is a gas, and the steam is used as the form of state of water, and also our ethene is going to be gaseous as well. Okay, so as well as having the phosphoric acid catalyst, we also need to know about the conditions, and the temperature at which it happens is about 600 Kelvin. Okay, so let's put 600 Kelvin down there, and also about 6,000 to 7,000 kilopascals. 6,000 to 7,000 kilopascals. You might see the reaction conditions as atmospheres in some sources, in which case this is about 60 to 70 atmospheres. Okay, so that's the individual reaction for making ethanol. Let's have a look at the reaction mechanism. So we start off by drawing out our ethene. And we're going to have hydrogen ions floating around from the catalyst, and the double bond is highly negative, and it's going to be attracted to an electrophile, all right, the hydrogen ion being the electrophile. All right, so although it's the hydrogen ion that does most of the attacking, the arrow goes from the bond to the hydrogen ion, and it's a curly arrow as usual. Okay, so that's the first thing that happens. The electrons in the pi bond attack your electrophile, which is the hydrogen ion, and you're going to make a bond. All right, so let's draw out that bond. So we're going to make a bond with one of the carbons. And we've made a carbocation. So let's just pause there and track a few electrons. Let's draw out the electrons that were in this bond. Let's draw them as red dots in that bond there, and let's circle this hydrogen ion in red. All right, that has become this hydrogen atom, and those bonds, those red dots that were in the double bond, the pi bond, right, have made this bond here, and which has left the second carbon atom here without one of its electrons, and so it becomes positively charged, and this is called the carbocation. So that carbon cation is positive, and that's going to get attacked by something negative that's floating around, which would be a nucleophile as it happens. And water is a good nucleophile, so let's draw our water molecule. So our water molecule with oxygen's lone pairs is inevitably going to be floating around, and the lone pair, this lone pair on the water molecule is going to attack that carbon atom that has the positive charge, and that's going to make a bond as well. So let's draw the product of that out. So we've still got the left hand side of the molecule still the same. Now we've made a bond with the oxygen, and the oxygen's now got 3 bonds, which is not a happy situation for the oxygen. But let's pause there again and track some electrons. All right, so let's turn these this lone pair of electrons into red, so we can track them, and they are the ones that make this bond here. Oxygen used to have both of the electrons in the pair, and now it's only really got one. It's sort of given one to the carbon, and so that leaves it with the positive charge there, which, as you know, oxygen is electronegative to start with, but when it's short of an electron, it's even more in need of electrons. Let's just draw oxygen's other lone pair in there. So it says to one of these hydrogens, it says, hang on a second, I want your electrons, and the electrons that were in that bond are going to be taken by the oxygen, which leaves a hydrogen atom without an electron, which is also known as a proton, to be ejected from the molecule. So let's draw that out. Including the lone pairs. Okay, and while we're at it, why don't we do our trick of tracking the electrons? Let's change to green this time, shall we? Okay, so the two electrons that were in this bond here between the oxygen and the hydrogen have become one of these lone pairs. Let's say it's this one. And this green hydrogen here has left, and that's what we're left with. We're left with an ethanol molecule and a hydrogen ion catalyst, which has just reformed the catalyst. And so now you have hydrated an ethene molecule that you started off with, using a hydrogen ion from the catalyst, and created an ethanol molecule at the end and reformed the catalyst. So let's have a look at the process now, the manufacturing process of hydrating alkenes. And the interesting thing here is that in industry we use a continuous process because although the reaction is 100% atom economy, let's just write the reaction out. So we've got our ethene, C2H4, and our steam or water. Okay, it's an equilibrium reaction, and we make our ethanol. Okay, and it's exothermic. It's about minus 45 kilojoules per mole. So you can see that there's only one product, ethanol, and so that's 100% atom economy, which is good, but the yield is only about 5% in a batch process. Okay, so that's no good for companies that want to make money out of making ethanol. So what they do instead is they use a continuous process, and the continuous process looks a little bit like this. We're just going to draw the schematic of it. So we're going to start off with our reactants, C2H4 ethene and our steam H2O, and incidentally we use for every 1 volume of ethene we use about 0.6 volume of steam. And these are the reactants. These are the reactants, and they get fed into a reaction chamber. And you'll remember the reaction conditions in the reaction chamber. So temperature wise we've got about 600 Kelvin, pressure wise we've got 6,000 to 7,000 kilopascals. We've also got phosphoric acid catalyst, H3PO4, and that's encased in silica pellets for surface area reasons. And so that's the reaction chamber. Right, so with those conditions, the reaction takes place, and you get an equilibrium mixture coming out of the reaction mechanism, which is going to have ethanol in it, but it's also going to have unreacted ethene and water in it as well. So first thing we need to do is separate out our ethanol. We're going to do that by condensing, because our boiling points of ethanol and ethene are quite different. So here we're going to have a condensation chamber. Okay, and let's draw it like this, so we get a little bit of liquid coming out at the bottom of this chamber. So the liquids coming out of there would be ethanol, but also water. We're going to condense water as well with it, which is not a problem. It just requires another step. But at the temperature of the condensation chamber, ethene remains a gas. Okay, and so the ethene comes out the side here and is fed back. So let's label this unreacted ethene. And so the fact that it's only a 5% yield on the first pass doesn't matter, because we take our unreacted ethene and feed it back into the reaction chamber, and there we have it, and we have ethanol and water coming out. So we need to purify that ethanol. We're going to do that by fractional distillation. Alright, until you get pretty pure ethanol. And other alcohols, propane 2-ol is a very common alcohol as well, used in industry. They are made in the same way. Okay, the other method of making ethanol is to ferment glucose. Glucose being grown in plants when they grow and they're harvested. For example, sugar cane or sugar beet are two of the main crops that are used to make ethanol. Starting off just with a little interesting story about wasps. Now, you don't really get stung in June, July, August by wasps because they're too busy doing their work for their hive. They tend to sting you later on in late August, September, in the autumn time, and that's because they're busy gorging on fermented fruit, i.e. drinking ethanol within the fruit, and they get a bit drunk and they get careless and start stinging people. So that's the story about bees. The middle picture here is a electron microscope picture of yeast. These are little yeast particles, and these are what are used to digest and then ferment the glucose into ethanol. So yeast, of course, are biological, and they are going to operate at a optimum temperature. So let's draw a little graph here of temperature against rate of reaction, right? So if we put temperature on the x, and let's just summarize that rate of the reaction. This is the fermentation reaction. Then when it's too cold, the yeast doesn't work very efficiently at fermenting the sugars, and the rate of reaction gradually increases as the temperature increases, and then gets too hot for the yeast because they're biological, and decreases. And so the optimum temperature that yeast like to operate at is about body temperature as it happens, but between 30 and 40 degrees C is the optimum temperature for yeast to work at. And so that's the temperature that industrial yeast fermentation processes work at as well. And this picture on the left here is an industrial scale vat that would be used to ferment sugars. And so what that low temperature, I mean 30 to 40 degrees is low for an industrial process. What that means is that the reaction can be quite slow, which is a little disadvantage. And the other thing to note about fermentation is that it's anaerobic. It happens without oxygen. So just summarizing what we need for the fermentation process: we need yeast, we need sugar, we need an optimum temperature of about 37 to 40 degrees, and we need no oxygen. They are the conditions we need in order to ferment sugars into ethanol. Okay, moving on. We're going to have a look at the various reactions that happen, and also start to talk about the carbon neutrality of biofuels. So one of the main uses of the ethanol that is made by this fermentation of glucose process is to go into fuels. You can put it into, mix it in with traditional fuels and make biofuel, and then burn it in your cars instead of 100% petrol, 100% diesel. All right, so a bit cleaner for the environment, so we think. And it is, in fact, it's just not quite as clean as we think. So we've got three pictures here. One's photosynthesis, one's fermentation. That's I think somebody's beer being made, and we've got the exhaust gases coming up the back of a car that's running on green biofuel. Okay, so let's consider the three reactions there. First of all, the fermentation reaction, which is to do with this picture. So fermentation. Okay, that's going to start off with let's say glucose. Okay, C6, H12O6, and that's going to make our ethanol. You actually get 2 molecules of ethanol for every 1 molecule of glucose. There's our ethanol, and in that process we get a bit of carbon dioxide given off. Okay, so that's the fermentation reaction, and we've made some ethanol. Let's put it in the car, and the car burns it, and so that's a combustion reaction. That's a combustion reaction. So when we're combusting our ethanol, let's see what reaction happens. So let's start off with 2 molecules or moles of ethanol. And we would need 6 moles of oxygen to combust that. And you're going to get 4 moles of carbon dioxide and 6 moles of water vapor coming off. Okay, so that's our combustion reaction for the same amount of ethanol. And so you can see now we've made 4 plus 2 moles of carbon dioxide for every mole of sugar that we grew. Now, when we were growing our sugars, we used photosynthesis, or at least the plants used photosynthesis. So let's write that reaction down. So the photosynthesis reaction very usefully starts off with carbon dioxide and water, and makes our sugars. Let's call it glucose, C6, H12O6, and a bit of oxygen for us to breathe as well. So just balancing it out, we need 6, 6 and 6 to make it all balance. And so now what you can see is that the photosynthesis process used up 6 moles of carbon dioxide, and the fermentation produced 2 moles of carbon dioxide, and then the combustion process produced 4 moles of carbon dioxide. So you can see minus 6 from photosynthesis is equivalent to the 2 plus 4 that we made when we fermented and then combusted the ethanol. Okay, so that's where the term carbon neutral comes from. That's where that term carbon neutral comes from, and on the face of it, it is carbon neutral, and it's certainly a lot more carbon efficient than digging our oil out of the ground and burning it straight off. However, it's not quite as carbon neutral as we think. And these pictures illustrate why it's not quite as carbon neutral as we think. What we've got on the left is some sugar beet, which is what in this country we make our bioethanol from. Countries like Brazil grow a lot of sugar cane, and that's what they use to make their biodiesel out of. But of course, to grow a large quantity of sugar beet means that you've got to use a load of fertilizers. Fertilizers need to be manufactured and installed onto the farms, and that takes a lot of energy. The fertilizers also wash off into our water system, which is not great for the environment. Also, the issue with growing crops for fuels is that is land that could be used for growing crops for food, for calories, because certain parts of the world are hungry, and to use the calories that we grow in order to burn is, in some people's view, a little bit immoral when some people are hungry in different parts of the world. Okay, so we also have a picture of actually British Sugar's bioethanol plant in Anglia. And I've got this picture up here because you can see that the process of fermenting and making the ethanol is going to require a lot of energy. Okay, so the energy that is required, not least in distillation of the ethanol from the water, because it's very dilute ethanol you get straight out of the fermentation process, and in order to concentrate it, you need to boil the mixture and evaporate off the ethanol. That requires a lot of energy, and that of course would use carbon dioxide if the energy source is non-renewable. Okay, so for those various reasons, biofuel is, let's say, good, but not it's not carbon neutral. So let's move on to a comparison of the ethanol production methods, and of course the two production methods are fermentation. So let's make a table of this. So we've got fermentation, and we can also produce it from ethene. Let's summarize that with ethene hydration. Okay, so let's just try and draw a table so we can compare. And first thing we're going to compare is the economic aspects. So when we look at fermentation, first thing you'll remember is that it's batch, right? Whereas ethene hydration is continuous. Fermentation is impossible to make continuous because it's a biological process, and the fact that fermentation is batch means that you have to empty the vessels, clean them before you restart the next batch, and then restock them with the raw materials each time. So this is inefficient. Whereas continuous processes are more efficient, and you can recycle your reactants, and so you're generally saving quite a lot of cost. All right, so let's put cost effective. Okay, so that's a little comparison of the manufacturing processes. Now in terms of the reactions, these reactions are slow. And although we're using the catalyst yeast to speed it up, we can't use temperature and pressure because the yeast want their own temperature and pressure, and they're not bothered about how it's as fast as they want it to be. And that's the limiting factor there. Whereas with ethene hydration, we can use a high temperature and make the reaction fast. Okay, so that would be an advantage of ethene production if you're in a rush to make your ethene. And so just summarising that, so we're going to have low temperature and pressure, where we've got high temperature and pressure. And in terms of labour is also an economic aspect. Fermentation is quite labour intensive. Whereas ethene hydration is mostly done with capital equipment, with plant and machines. So let's call this capital intensive. And which one's best depends on your viewpoint. If you're trying to create employment, then labour-intensive activities are good. Whereas if you're trying to maximise return on investment, generally capital-intensive operations are better. In terms of the purification of the product, you need to purification And with fermentation, it has to be done by distillation. So whereas with the hydration of ethene, the ethanol is pretty pure to start with. Let's call it 98%. Now there are some needs that need it to be 100% pure, but for a lot of uses 98% purity is good. So straight out of the continuous process you can start selling and using your ethanol, and it's only a small amount of it you need to purify further, whereas with fermentation you have to purify all of it, and you do that with distillation. That uses energy and therefore money. Okay, so let's then compare environmental. Aspects. If we compare environmental aspects, fermentation uses renewable resources. The definition of renewable is that they can be grown within someone's lifetime, and so sugar beets grown every year, sugar cane's grown every year, harvested and grown every year, whereas crude oil is non-renewable because that takes hundreds of millions of years to make. So let's just summarize that by calling crude oil non-renewable. Summarize that like that. However, the land is used, which could be used for crops, and this does not require any land. So that would be an advantage for ethane production. So as far as an exam question is concerned, what's important is not really which one you think is best, but what's more important is that you can compare the pros and cons of the two methods. So hopefully you have enough information there. So that brings us to the end of our little video on ethanol production, and we looked at our two methods of making our ethanol, hydrating alkenes from crude oil or fermenting glucose that we've grown. And we've compared the pros and cons of those as well. And we've also had a look at the issues of biofuels and just established that it's not quite carbon neutral when you consider the processing that's involved in making it. Okay, hopefully that's been clear.